Hello students, in the series of properties of Fourier transform, three more properties needs to be discussed. So out of these three, the first property is duality property. The duality property says that if ft has a Fourier transform f omega, then capital F of t is the Fourier transform of 2 pi f of minus omega. So to prove that, we need the formula for inverse Fourier transform, which is f of t is equals to 1 by 2 pi minus infinity to infinity f omega e raised to the power j omega t d omega. So this expression replace t by x. So we have two t's in this expression, both the t's will be replaced by x. So f of x is equals to 1 by 2 pi f omega e raised to the power j omega x d omega. Now replace omega by t. So again we have two omegas, both the omegas will be replaced with t, so it will become fx 1 by 2 pi ft e to the power jxt dt. Now finally replace x by minus omega. So this x will be replaced by minus omega, it will become f of minus omega, this will be 1 by 2 pi, this is minus infinity to infinity ft e to the power minus j omega t dt. Now we will take this 2 pi here, so it will become 2 pi f of minus omega, and minus infinity to infinity ft e to the power minus j omega t is nothing but the Fourier transform of this particular function f of t. So we can say Fourier transform of f of t is 2 pi f of minus omega. So this way we can prove this duality property. The application of duality property is to calculate the inverse Fourier transform with the help of properties. We will take some numericals based on properties, then you will be better and have a better understanding of this property, why this property is used and how it is basically used to perform the various operations of Fourier transform. Okay, so after this duality property, the next property is time differentiation. So the next property is time differentiation property. The statement of time differentiation property says that if ft has a Fourier transform f of omega, then dft by dt has a Fourier transform j omega f omega. That means if you differentiate the function ft with respect to time, this Fourier transform will be multiplied with the term j omega. And dnf by dtn, that means if you differentiate this above thing with in n times, then j omega to power n f omega. That means this j omega term will get multiplied how many times you will differentiate this equation. So let us see the proof of this particular property. For the proof, we will take the inverse Fourier transform formula again, that is ft is equals to 1 by 2 pi minus infinity to infinity f omega e raised to the power j omega t d omega. Now differentiate this equation with respect to t. So this will become dft by dt. This will be 1 by 2 pi, it will remain same, only e to the power j omega t will be differentiated with respect to t. So that means d by dt e to the power j omega t d omega. So what will be the differentiation of e to the power j omega t? It will be j omega e to the power j omega t. So I have written this. Now I can write j omega outside this. So j omega, then 1 by 2 pi minus infinity to infinity f omega e to the power j omega t d omega. This whole thing is nothing but f of t. So I can write dft by dt is equals to j omega ft, or I can write dft by dt has a Fourier transform j omega f omega. Again I am telling you, this bidirectional arrow is what? It says dft by dt has a Fourier transform j omega f omega. Okay, so I hope you understand the concept of time differentiation property. Now the same way we will see frequency differentiation property. So the next property is frequency differentiation property. So same as time differentiation property, we will see frequency differentiation property. In this, if ft has a Fourier transform f omega, then minus jt ft has a Fourier transform df by d omega. For the proof, we will take the formula for the Fourier transform instead of inverse Fourier transform. So the formula for Fourier transform is f omega is equals to integration minus infinity to infinity ft e to the power minus j omega t dt. Now we will differentiate with respect to omega. So it will become df by d omega. Again in this expression only this term will be differentiated with respect to omega. So I have written f of t d by d omega of e to the power minus j omega t dt. So differentiation of this will be minus of jt will come outside and it will become e to the power minus j omega t and dt. So this minus dt I will keep outside the integration. It will become minus infinity to infinity ft e to the power minus j omega t dt, which will be df by d omega is equals to minus jt f omega, where f omega is the Fourier transform of ft. So if I write this ft, I can write it in this way: minus of jt ft has a Fourier transform df by d omega. So this way frequency differentiation property can be explained.